Hi everyone, I'm Zhiqiang. Today I want to talk about refining fitness function for search-based program repair. First, let me introduce the search-based automated program repair. GenProg is an early API tool which uses genetic programming to search for a modified program which can pass all test cases. As you can see in the diagram below, the input of the search process is a buggy program and its test suite. It goes through an iterative repair process and output the test adequate patches. In each iteration of the repair process, the patches are selected and modified and finally validated by the test suite. During the iteration, a fitness function is used to select better patches. Now let's have a look at the conventional fitness function introduced by GenProg. The input is the Boolean test result from each test case, which is either passed or failed. So a better patch always has more passing test cases. Assume we have several different patches which fail the same test case. Maybe they failed in different ways, like testing timeout, wrong assertion values, or stack overflow. However, the conventional fitness function doesn't care about a test case failure. Thus, we cannot distinguish the patches using the conventional fitness function. And that can lead to the low fitness diversity, which creates large plateaus in the search space. So it might be inefficient to find better patches with the conventional fitness function. And the motivation of this research is to refine the fitness function to have higher fitness diversity and a smoother fitness landscape, which should be more efficient at finding test adequate patch. We propose a more fine-grained fitness function called two-phase. In the first phase, we always prefer patches that pass more test cases, just like the conventional fitness function. While in the second phase, we only compute distance between the expected and the actual output of test case failures when we're comparing patches with the same number of passing test cases. Here are 3 examples of the distance metric. If the wrong output value is Boolean, or the test is timeout or crashed, then the penalty for this test case is a max integer. And for numeric outputs, the assertion distance is the absolute difference between the two numeric values. And for a wrong string output, we compute the Levenshtein distance between the 2 strings, which is the minimum edits required to make the string the same. Please note that all the distance here will be normalized into the range of 0 to 1 and aggregated for each patch. Here is the research that related to the fitness function. GenProg is the conventional fitness function, and ARJAe is the most similar work to ours. They also used assertion distances, and their research has given many useful insights on implementing the distance metric which I introduced in the previous slides. The differences are that ARJAe does not prioritize the number of passing test cases, and they penalize the failing test cases which passed by the original faulty program. Another work inserts the checkpoints around numeric values to log the intermediate program states. And some other fitness functions have used advanced technologies like a learned environment and a word embedding models. In this research, we compare the two-phase fitness function against the ARJAe and the GenProg fitness function. Last year, in our position paper, we have proposed to implement the fitness functions with the Gen framework, which is an extensible and modifiable program repair toolbox for Java programs. And we propose to use the same parameters as the one used by the latest GenProg work. So it's 10 generations, 40 individuals, repeat 20 times, and we use the GenProg search functions. We also apply the statement and expression level edits. For the benchmarks, we selected 16 of the 40 programs from the QuixBugs dataset. It provides 8 types of bugs and the 3 types of failures. Here are the 3 research questions. The first one is that how effective are the various fitness functions at providing a diverse set of patches, thus avoiding large search pallettes? The second question is that how effective and efficient are the various fitness functions at finding test-adequate patches? The last question is that how well do the test-adequate patches generalize to unseen tests? Here's the result for research question 1, search pallettes. Let's first look at the diversity of the patch generated, which is the average percentage of patches that have at least one other with the same fitness. And we found out that there's no significant difference between the 3 fitness functions. Then let's have a look at the quality of the patches. It is about the percentage of patches that has better or equal fitness than the original 40 program. And we found that the conventional fitness function produced 2 to 3% more better patches for 3 QuixBugs functions. So overall, the conventional fitness function is better than two-phase and the ARJAe for this research question. And the results of two-phase and ARJAe are very close. For research question 2, we also look at 2 factors. The first one is the number of runs, and that produce at least one test-adequate patch. The conventional two-phase and ARJAe fitness function has produced at least one test-adequate patches for respectively 10, 8, and 7 programs. And now let's have a look at the number of test-adequate patches produced in total. So the conventional fitness function has found more for most programs, while two-phase and ARJAe are similar. For the second factor, let's look at how unique are the test-adequate patches. We define a patch as unique if it has a unique sequence of edits. So in this research, the semantic equivalent patches are also different. And we found that the patch uniqueness for most programs are over 80%. Even the lowest one has 65% of patch uniqueness. And the results for the 3 programs are similar. We also find that most programs can be found by any fitness functions in the first generation. In addition, only 3 40 programs requires more than one edit. We know that test-adequate patches can be incorrect due to the test overfitting problems. So in research question 3, we validate those patch correctness in 2 steps. The first step is through an evil suite generated test suite. And the second step is that we manually check those patches against the ground truth version. And only the simplest patch are validated. The simplest patch are the one with minimum edit, because we know that QuixBugs program only have single line faults. And in this research question, we do not consider differences between the 3 fitness functions due to the limited research time. The result of the research question 3 is that among the 1640 programs, the Gene framework have produced test-adequate patches for 11 programs. 10 of 11 has passed the evil suite generated test suite, and 8 programs have been manually validated to be correct. And 2 programs have not reported to be fixed by existing API tools. As you can see here, Gene is very effective at fixing the QuixBugs program compared to other API tools. In conclusion, more fine-grained fitness function, two-phase and ARJAe are no better than the conventional ones on the subset of QuixBugs dataset, which is against the result of the related work. Conventional fitness function has higher fitness diversity, and it's more effective at finding at least one test-adequate patch. So in the future, we want to evaluate on the complete set of QuixBugs dataset and other benchmarks like defects for J to mitigate the biases.
The chat, so that's only people in backstage can talk to each other in the audience. And I think we're live now, aren't we? Are we live? Can someone say in chat if we're live or not?
Do we have a private chat section?
Yes, but we're not private now. Everyone is listening to us now. I can tell you later when to find it.
I think you guys are live.
Cool.
So let me start with some questions for to get the discussion started. So I have, I think that is interesting, like that the results that you have showing that the conventional fitness functions actually did well compared to other the newer kind of fitness kind of function that is being proposed, like more complicated ones using different distance metrics. Any insights on why particularly the conventional methods has leads to, for example, higher fitness diversities? That.
Zhang Americ, I want to give you priority.
Hello, can you hear me?
Yes.
Okay, so I think one reason is the QuixBugs dataset we're using. It's actually a pretty new dataset. It's a small and concise programs with single line faults. So I think that might lead to that. So the fitness doesn't explore too much search space. So the conventional fitness function is better than the two other ones. So maybe if in the future we try different data sets, then we will have like more insights into the differences.
Okay, so your kind of answer is more like centered in around the benchmark that is being used. Actually, it's leads me to my next questions. Like, do you think that for different benchmarks you will get the?
That's a very nice question. Since we haven't tried a different benchmark, I would say it could be different, but I'm not certain about it because we need experiment to show it.
Yeah, just to add, I agree. We definitely need to run on bigger software, maybe larger search space. I don't know. It is interesting actually that it did occur, right? That it wasn't that there wasn't much difference. I can't say we look into details yet, but we do plan to. Like kind of extending in two directions. One is just bigger benchmark sets to see if we have more diversity there with the search space. I would imagine would be larger. And the second dimension would be just to try to characterize the search space in a more formal way. I know. Recently I've worked from the search-based software testing field when they used. I mentioned it, but then I don't remember exactly the details. But it was by Gordon Fraser and his group, where they try to characterize the search space of search-based software in testing, but like using more formal ways rather than what's been done in APR, as in just running lots of code and looking for mutational robustness or neural landscapes and stuff like that. So we do plan to extend in those two directions just to understand what's going on there.
Okay, I see. So from the perspective of, because you mentioned about, I'm not really sure about the definitions of fitness diversity, because I think in terms of like mutation testings, like I think it's more on like different kinds of bugs that it models, but I think in genetic algorithms, like the fitness diversity is different. Can you explain the difference?
Yes. So,
Okay.
so fitness diversity means like different patch. I mean, probably should have different fitness. Yes, that's what I mean. So when the patch is different and we expect the fitness also to be different, then we can search for the better ones. So if the different patch have the same fitness, which means the low diversity, then the search function is hard to guide to search for the better patches. Yeah.
Mm-hmm. Yeah, that is actually kind of a difference in terms of, do you think that other kind of diversity will be helpful in like guiding the patch towards generating more correct patches? Like if we trying to increase the diversity in terms of like what are the types of repair operators or mutation operators that's being used, for example?
Our paper focus on the fitness diversity, but we also tried some new operators. Justina, do you want to go with it?
So honestly, like, thank you for the question. Yeah, that is true that there are different diversity metrics. To be honest, we haven't looked into it, but maybe that's what the results are telling us, that maybe we should look for different measures of diversity than what we proposed thought would work. I know, America, if you want to add
if I can try to clarify a bit much, we are not really interested in diversity in terms of patch, in terms of generating more diverse patch, but diversity in terms of fitness value, meaning that if you have two patch, we want them to have slightly different fitness value in order to compare them and to prefer one to another. So it's really diversity in terms of fitness values to guide the search rather than diversity in terms of patch so to generate. It's really more of a guidance tools rather than a diversity guidance tools.
Mm-hmm.
The whole point is just to smooth the fitness landscape so that hopefully the search algorithms would work better, be guided better.
Okay, thanks for the answers. We can take, maybe there are only 5 or actually very few seconds left, so